Hello everyone, this is Dan O'Brien, IAC Acoustics Industrial Business Unit Manager, and I'll be giving a brief webinar this afternoon on IAC Acoustics Noise Shield Outdoor Noise Barrier Panels. And during that webinar we'll have some time for question and answers. You can use the GoToWebinar application to post questions, and I'll try and make sure that I address all of the ones that come up. We had a little over a dozen registrants for the webinar, and I'm going to give people a couple of more minutes to join us. So if we just sit tight for a few moments here, I'm going to wait for a couple more people to log in, and then once they've done that, we'll get going. If you've got any questions or there are any issues, right now I'm going to send out like a quick chat to everybody to let everyone know that we're getting ready to start, and to ask to make sure that they can see the screen and hear my voice. If you could just reply to the chat request, that would be great. Okay, great. Welcome everyone to IAC Acoustics webinar on Noise Shield Outdoor Barrier Screens. My name is Dan O'Brien, and I'm IAC Acoustics Business Unit Manager for the Industrial Systems. And I'll put a little bit of contact information up on the screen there. You can feel free to either write that down, or if you'll send me an email after the presentation, I'll be happy to send you any additional information that you might like, and we can actually follow up and go through any questions that you might have at the end of the presentation. If there's anything that looks like it's going to take a little bit longer, I'll be more than happy to go through that in as much detail as you'd like after the presentation. The presentation is going to last about 25 to 30 minutes, and in the presentation we're going to cover how noise shield screens solve noise control problems, how to choose the appropriate noise shield barrier screen component for your application, and then how to describe and specify noise shield products and how they're installed. And then also we're going to provide you with some additional resources that you can use to gather additional information for projects that you might be working on. We'll cover IAC Acoustics company information, some basic acoustic and screen terminology. We'll talk about IAC's noise shield panel types and performances, and talk about different screen applications. I'll show you some information on the IAC Acoustics website, and then we'll have some time for questions and answers. IAC Acoustics is currently owned by SoundSeal, our parent company, that was founded in 1978 as United Process. SoundSeal is a manufacturer of flexible products for noise control, such as sound curtain panels, floor underlayments, and they also make acoustical wood ceilings and fabric wrap panels. They operate out of a Western Massachusetts location in Agawam, and they're on the web at www.soundseal.com. IAC Acoustics was actually founded in 1949, so we were quite a bit older as a company, and we were founded as Industrial Acoustics Company in New York City. IAC Acoustics has been focused on sheet metal systems for noise control applications and architectural acoustics since then. We were acquired by SoundSeal in 2015, and currently we're operating out of a North Aurora location in Illinois, about 45 minutes southwest of Chicago. So it's a very nice central location for covering all of the United States from that one facility where we have all of our engineering resources, the vast majority of our manufacturing capability, and our salespeople as well. We're on the web at www.iacacoustics.com. And we provide on the website lots of different product information and literature if you're looking for any additional material on the IAC noise shield panels. IAC Acoustics noise shield barrier panels shield people from loud equipment and transportation systems by forming a screen that blocks and absorbs sound energy. Acoustic screens protect receivers by blocking the direct sound path. If you imagine a roadway and a house, there's lots of direct sound energy that travels immediately from the car and the engine and the exhaust and the wheels without any obstruction whatsoever towards people living in the house. Once a barrier is put up that blocks the line of sight, the barrier prevents noise from going directly through it, and the sound has to travel a much longer path and go up to the top of the barrier, bend over it, and then come back down. The noise that takes the longer path is greatly attenuated, meaning that people in the house are now exposed to a much, much lower sound level. The key here is that the line of sight must be interrupted, and the angle that the sound has to travel through when it goes from the source up to the top of the barrier and then down to the receiver is important. A sharper angle means a better performing barrier. When we're talking about barrier performance, we're talking about taking a sound and attenuating it or reducing it, making it quieter. So really what we need to do is kind of start off with some sort of sense of how loud a sound might be and what sort of difference we're hoping to achieve. People have an incredible range of hearing. We can detect sounds from 0 decibels, which is our theoretical lower limit of hearing, all the way up to 120, 130, and 140 decibels. One of the important things to understand is that those measures are not linear or arithmetic. They're actually exponential. So a doubling or halving in sound energy doesn't just mean that you're going from 40 dB to 80 dB. A doubling or halving of sound energy means that you're adding 3 decibels or subtracting 3 decibels. So for example, normal conversation at 1 meter might be 60 decibels, and if you doubled the number of people that were speaking at the same time, it's not going to go up to 120 decibels, it's going to go to 63 decibels. That's important when we look at the differences that a barrier can make and we start to try and understand what that difference in sound energy is going to feel like, how we're going to experience it. The most important things to understand are that human beings have an incredible range of hearing and that we use a special weighting factor called A weighting to reflect the fact that people don't hear equally at all different frequencies. Human beings hear better in the mid frequencies and much, much worse at the low frequencies. So if we took a measurement of some audio or acoustic experience with a perfect microphone, the total that the perfect microphone is measuring may be more or less than what we might experience as a human. We use the dBA designation to indicate that that weighting has already been applied to the measurement so that the numbers are reflective of what a person would experience. I'm going to play several different audio clips, and these are just static or pink noise, and what we're going to do here is convey the difference between an attenuated level and the standard level. I'm going to start just with some pink noise. And now if we drop it by 3 dB, and you'll remember that that's 50% of the sound energy, you'll see that it's just perceptible. Even if we now reduce that sound level by 3/4, it's still really a relatively minor difference. When you're dealing with noise control problems, usually people are complaining because there's some unwanted noise that they want to eliminate, and they're looking for a much more dramatic difference. And that might sound more like a 10 dB or a 20 dB reduction. That's 10 dB. One more time. And here's a 20 dB reduction. So keep that in mind when we start to talk about barrier attenuation and how much of a difference a barrier screen can make. Another key parameter when you're looking at the performance of barriers and designs for barrier components is frequency. Usually the noise that you're trying to attenuate with a screen exists at lots of different frequencies, high frequencies and low frequencies. And that means that the noise is going to have a combination of short wavelengths and long wavelengths. And this is important because not only do people hear differently at different frequencies, but materials behave differently at different frequencies. Something that's a very good barrier to sound at a higher frequency may not be such a good barrier to sound at a lower frequency. When we're evaluating the design of the screen and the materials we're going to use to construct the screen, we have to take a look at the acoustic properties of these materials at a range of different frequencies. And to just kind of illustrate what some of these frequencies sound like, I'll play a couple of clips here as well. A relatively high-pitched sound, around 8,000 hertz, would sound like this. A much lower pitched sound, around 63 hertz, would sound like this. We can hear the entire range of frequencies in between. And the key is that the materials the barrier are made with are going to work better at some frequencies than others for blocking and absorbing sound. This means that when we evaluate the materials, we have to test their acoustic properties at a range of different frequencies. And the most important material property or acoustic property for a barrier is the sound blocking capability, or the transmission loss, which is a number that's given by frequency. So a lab's constructed with the wall separating two rooms, a source room and a receiving room. A loud noise is played in the source room. The test material samples installed into an opening in the wall between the source and the receiving room. And microphones are used to measure the levels on either side of the test material. The difference between the levels, the relatively quiet side on the receiving side and the relatively loud side on the source side, that delta is the transmission loss at a particular frequency band. We take measurements at the full range of octave band frequencies and then evaluate those differences with some standard curves for sound transmission class rating, and that allows us to assign an STC rating to the test material. In general, a bigger number is better, and as a comparison, a 2x4 drywall system with no insulation would have an STC rating of 34. And that's a relatively modest acoustic barrier system. When you're constructing a barrier, one of the issues that you can sometimes have is that the barrier, if it's too reflective, will simply redirect sound energy in a new direction. So you may protect people in the house across the street from the source, but if you put that barrier up, you might now be just redirecting the problem to a new location and creating an issue for neighbors on the other side of the street. So it's important that the barrier material absorbs sound that strikes it, not just block sound going through it. And we have to measure that sound absorptive property at a range of different frequencies as well. We measure the sound absorption coefficient, which is basically a percent of the sound energy that's striking a material that's absorbed by the material, and evaluate the performance at a range of frequencies to come up with a single number rating the noise reduction coefficient, or NRC. It's expressed as a decimal, and the bigger the decimal, the better sound absorber the material is. Because of the math that's involved and because of the size of the test element inside the lab, sometimes you can get numbers that look a little bit counterintuitive. So you can get NRC ratings that can be above 1, even though that's really not possible in the real world. So in general, anybody making acoustic calculations would limit the amount of sound energy that they're calculating to be absorbed. So that would certainly be a lot less than 1. But sometimes the math will indicate those numbers. Now, as an example of a barrier screen system, if we looked at a 15-foot tall barrier, and we looked at the 15-foot tall barrier 8 feet from the source and 32 feet from the receiver, and we assume that the source is about 4 feet above grade and the receiver is 10 feet above grade, maybe they're on the second story of that building, and the barrier height's 15 dB, we can come up with some rough estimates for the performance of the barrier by frequency. And they would range from 5 to 10 dB in the lower frequencies up to a limit of about 22 dB in the higher frequencies. It's important to keep in mind that the combination of the spectrum of the source sound energy and the insertion loss is going to determine the overall attenuation. Typically, that overall attenuation for a barrier screen will range somewhere between 10 to 15 dB. And I'll give you a little demonstration right now how that barrier performance can change by varying position of the screen and varying height of the screen. So this is a similar configuration to what we had before. And we can see that if I've got a little schematic here that kind of indicates the path that the sound has to follow across the top of the barrier, while we start to change some of these numbers, while we position the source 8 feet from the barrier, the receiver 32 feet from the barrier, the height of the source at 4 feet, the height of the receiver at 10 feet, and then the height of the barrier at 15 feet, we're going to get a theoretical barrier performance that looks like that graph over on the right. We're reaching a maximum limit of about 22 dB in the higher frequencies, because even though the theoretical attenuation might be higher than that, in practical terms, you're really not going to achieve a much higher result than 20 to 22 decibels. If we start to change some of the barrier parameters, let's say that we move the source so that it's further away from the barrier. Instead of it being 8, it's 32. You'll see that that path now, that angle across the top of the barrier, is decreased, and you'll see that the barrier performance in the low frequencies and the mid frequencies is also decreased. So you have to keep in mind that one of the most important things when you're designing a barrier screen is the position of the barrier and the height of the barrier in relation to the source and the receiver. If the barrier's got to go in the middle, you can always compensate for that by making the barrier taller, but that's going to make the barrier more expensive as well. Any questions on any of the information so far? Feel free to post them in that questions pane. I'm keeping an eye on it here, and I'll be happy to try and answer them either as we go through the presentation or at the tail end right before we wrap things up. In addition to acoustical properties, the barrier panels have to have some structural capability. They're going to be resisting wind and seismic loads, and you really want to have a barrier that's going to do a good job of blocking sound from going directly through it, as we could see down here, and then also sound that's going to travel across the top of the barrier. So we're really looking for sound transmission loss properties of the barrier to be such that you're going to get an STC of 30 to 33 with some decent transmission loss in the lower frequencies. You're also going to be looking for some noise reduction coefficient or sound absorbing capability. Ideally, those would be around 1. And the panel would have the structural capability to withstand some wind load. IAC's panels can withstand up to 41.5 pounds per square foot at a span of 16 feet. And we can actually produce panels that have a much, much greater length. We can go up to a 20-foot panel, but because the panel size is longer, we've got a lower capability for wind load, so then it's only going to be 26 pounds per square foot. We have performance data for all of our panels listed in our data sheets and on the website. And you can see that the most common panel that we use, IAC's Noise Shield FSS panel, has an STC rating of 30, and it has minimum transmission loss values of 21, and they range up to transmission loss values as high as 40. So this is an excellent material and an excellent component to use for a barrier screen. We don't need a super, super high performance sound blocking capability because remember, some of the sound is going to go over the top of the barrier, and really you're not going to get, you may not get all of the benefit that you're looking for. As far as the sound absorbing capability, again, our barrier panels have NRCs that are very, very high, from 1 to 1.05, so they're going to work really well to absorb sound on the source side of the system. We do have test data for all of our panels and all of our acoustic performances that we're happy to supply for projects. And you can see that the panels all are very, very simple to construct and simple to install. IAC's most commonly used panel, the Noise Shield FS, is a 5-inch thick panel constructed with a solid 14-gauge material facing the receiver and a 20-gauge perf side facing the source. We also offer a special detail, the Continue line, which has a 5-inch, the same 5-inch thickness, but it allows for a completely concealed column detail and a very, very nice architectural appearance. We can also offer a Slimline panel, which is a 2.5-inch thick surface mount option, and then a Noise Shield SFS panel, which is 5 inches thick. It includes a septum layer in the middle, and it offers absorption on both sides. Lastly, we have a Noise Shield FST panel, which has some added mass in the interior of the panel that provides enhanced low-frequency transmission loss. The panels are available both in steel and aluminum, either unfinished or with a very, very durable powder coat finish. The panels are designed to be dropped into the pocket of a wide flange post from above. They're very simple to install. That pocket is 5.5 inches deep, which gives a little bit of clearance for the panel when it's installed. And we can come up with alternate installation configurations on a project-by-project basis. The most commonly used configurations use a wide flange beam with a 5.5-inch pocket, but we can also supply tube shapes that have angle iron welded onto the side. And when we have a very, very deep beam, sometimes necessary to resist higher wind loads, we can add an angle into the web of the beam. We're also able to integrate doors, both single leaf and double leaf, for access into the interior of an enclosed area. We can provide the full kit of all the necessary steel detail, the doors, the hardware, and the filler panels in order to complete the system. Common applications for the Noise Shield barrier panels include HVAC equipment, both rooftop mounted and ground mounted, lots of different types of machinery and equipment such as transformers, pumps, valves, engine generator sets, really any noise producing equipment that needs to be screened and shielded from neighbors. Transportation systems are also a very common application, as the panels can be used to form screens that shield neighborhoods and communities from rail lines, railroad yards, highway systems, and airports. For the Pasadena, California light rail system, IAC Acoustics supplied several different projects. They all included 16-foot long bays, 98 inches high, with the 14-gauge solid skin facing the receiver and the perf skin towards the rail line. They were all powder-coated with an anti-graffiti additive so that the panels could be cleaned without damaging the powder coating. You can see that we were also able to supply the support columns powder-coated to match the panels for an attractive appearance. The continue line detail that I mentioned earlier allows for the columns to be completely concealed behind the panels. You'll notice in these midsections right here that the column's invisible, and what you have is a very nice rectangular reveal pattern that allows for a nice uniform high aesthetic. We can also make penetrations in the panels, allowing for lighting and fixtures to be attached to the solid side. The continue line configuration utilizes a slot cut in the end of the panel that allows the panel to ride down the front face of the wide flange shape. So the continue line panel does not need a 5.5 inch deep pocket, but it does need a smooth vertical face to capture that slot in the end cap. They're very popular in New York City because they allow for the system to be installed with a nice attractive appearance that can sometimes be an issue for people living across the street in apartments. We can also supply custom filler panels for areas where ductwork, wiring, or penetrations need to be made through gaps in the panels. In addition to the continue line, IAC can supply noise shield slimline panels, which have a narrower depth, a slightly lower wind load rating. They offer the benefit of being able to surface mount to existing steel through self-tapping tech screws through the top and bottom tabs on the panels. They can also provide a very attractive appearance. You still do see a vertical reveal here where the two panels butt together. And the advantage of the slimline configuration is that if there's an existing set of support steel, we can utilize that to mount the panels. All of this information is available in IAC Acoustics Noise Shield Outdoor Noise Barrier literature, which we've updated for 2016, which we've made available on our website. And it contains performance data, specifications, and cutaway views of the different products. Additionally, on our website, you can find formatted 3-part specifications, panel drawings, and case studies of past IAC Acoustics projects. Should you need any additional information, you can feel free to contact either myself or our 2 regional salespeople, Mark Smith or Mark Simnick. That covers my webinar. If there are any questions that anyone has, I'd be happy to answer them now and see if there's anything else that we might be able to assist you with. I have a question from the audience that was asking for information about anyone that could assist in California, and IAC Acoustics works with Pacific Sound Control in the Los Angeles area. And you would certainly be able to get a hold of them, and I can actually just give you their phone number here. if you'll just hang on a second. So again, that was in the California, Los Angeles area, Pacific Sound Control. And their phone number is 714-892-6022. They're IAC Acoustics representative, and they would be happy to assist you with any noise control problem, as well as designing and installing any sound barrier systems like this. I also have a question from the audience that involves the sound absorption coefficients and some of the values that might have been greater than 1. And that certainly can be the case. Sometimes during testing, because of the limited sample size and the potentially small room that the tests are conducted in, the math that's involved doesn't give a completely accurate representation of how much sound absorption is taking place. Let's see if I can get back to some of that data there. And what we do is simply report the lab data that's present. So if you look at the sound absorption coefficients on this screen, at the 250 and 500 hertz and 1 kilohertz octave bands, you do see numbers that are higher than 1. In practice, those numbers would be limited for calculations to less than 1. Are there any other questions from the group? If there aren't, I want to say thank you to everybody for attending and watching the webinar, and please be sure to check out our future webinars and also to check on SoundSeal's YouTube channel for this webinar and our Did You Know video series. Thanks again, and if anybody else is looking for any additional information, please feel free to send me an email or give me a call. Thank you.